Can we travel faster than light? Imagine this. A single beam of light leaves the sun, racing through the silent vacuum of space at 299,792 kilometers per second. In just over 8 minutes, it hits your face on Earth. For centuries, we've worshipped this number, the cosmic speed limit, the speed beyond which nothing, no rocket, no signal, not even thought itself, can outrun. But what if that's not entirely true? What if somewhere in the far reaches of physics, there's a loophole, a way to bend, twist, or even break this rule? Imagine a ship leaving Earth and arriving at Alpha Centauri 4.3 light-years away, in weeks, not decades. If we could do that, it would mean rewriting not just the laws of motion, but the laws of reality. And yet, some scientists believe it might be possible. Others warn that the very idea could tear apart everything we understand about time, causality, and the universe itself. This is the story of our race against light, and the dangerous, beautiful dream of going faster than the universe says we can. To understand why faster-than-light travel is such a monumental challenge, we need to go back to the early 20th century, to a young patent clerk in Switzerland named Albert Einstein. In 1905, Einstein published his special theory of relativity. It wasn't just another scientific paper. It was a declaration that space and time were not separate entities, but a woven fabric, space-time. And in this fabric, the speed of light was the ultimate limit, a constant for all observers, everywhere, no matter how fast they moved. The faster you move, the more time slows down for you. The faster you move, the more massive you become. And if you could somehow reach the speed of light, your mass would become infinite, and time for you would stop entirely. That meant any object with mass, like a spaceship or you or me, could never actually hit that speed. The energy required would be infinite. It seemed final, case closed, humanity grounded. And yet, from the moment Einstein's work became public, dreamers, scientists, and science fiction writers began searching for loopholes. Because the universe might be vast, but human imagination is larger still. Before scientists seriously entertained the idea, storytellers did. In 1966, Star Trek introduced the warp drive, a way to stretch space itself, moving a ship without violating relativity. It was a work of fiction, but it planted a seed. Could bending space-time be the answer? In the decades that followed, novels, films, and TV explored concepts like hyperspace, wormholes, and tachyons, theoretical particles that always move faster than light. Fiction gave the public the vocabulary. Physics would need to give it the reality. In 1994, Mexican physicist Miguel Alcubierre published something extraordinary, a mathematical model for a warp drive that didn't technically break the laws of physics. Instead of accelerating a ship to light speed, Alcubierre proposed expanding space behind it and contracting space in front of it. Inside this warp bubble, the ship wouldn't move faster than light relative to local space, but the space around it would move, carrying the ship like a surfer on a cosmic wave. The catch? The energy requirements were absurd, on the order of the mass energy of the planet Jupiter. And worse, it needed negative energy, or exotic matter, something that has never been proven to exist in usable amounts. Another possibility comes from Einstein himself alongside physicist Nathan Rosen, the Einstein-Rosen bridge, better known as a wormhole. Think of space-time as a sheet of paper. If you fold it so that two distant points touch, you can step instantly from one point to the other. Mathematically, general relativity allows these structures. But there's a problem. They're unstable. Without exotic matter to hold them open, they collapse faster than light can pass through. At the smallest scales, the quantum world sometimes appears to break the speed limit. In quantum entanglement, particles separated by vast distances seem to communicate instantly. Einstein himself called it spooky action at a distance. However, no usable information can be sent this way, meaning it's not a ticket to FTL travel, yet. But it does hint that nature has strange pathways we don't fully understand. Even if we could travel faster than light, relativity warns us of bizarre side effects, the most unsettling of which is time travel. If you move faster than light relative to someone else, from their perspective, you could arrive before you even left. Faster than light travel wouldn't just be an engineering challenge. It would be a philosophical earthquake. But here's where it gets complicated. Some physicists believe we'll never, ever outrun light, not because it's technologically impossible, but because it may be fundamentally meaningless. The argument goes like this. The universe has given us a maximum speed because it's woven into the logic of cause and effect. Breaking that speed might be like trying to divide by zero. The question itself stops making sense. Others point out that the most promising FTL ideas, warp bubbles, wormholes, all require energy or matter we have no proof can exist in stable form. Without them, these concepts may be beautiful equations, and nothing more. And then there's the unsettling possibility. Maybe the universe already has faster-than-light travel, but it's happening in ways we can't see. Dark matter and dark energy dominate the cosmos, yet remain invisible to us. Could the real travelers be forces and particles we haven't even discovered yet?